Okay, Conrad. You have to unmute yourself and reactivate your video, probably.
Hey everyone, this is a good pointer. Romeo mentioned it already. We are recording this session, so if you want to speak and want to make yourself visible with video, you have to reactivate it now because the recording disables it for all. So if you feel comfortable, then show your face. Welcome everyone to today's monthly call. I'm excited that we have a focus topic today with Marc Rußwurm, who will talk about implicit neural representations. But before we dive into that, we have a couple of housekeeping things to do. Hopefully you know all our HackMD notes. You can go there to see details. So let me also post that. I think that happened already. You can see it in our channel. Join it there, and let's see what we have on the agenda today for this. So first of all, one thing is we have a web page called Earth2Vec GitHub.io. Let me also post that in the channel here for you. And if you go there, it's currently a basic web page, just having the link with our YouTube recordings of the monthly calls. And everyone is welcome to join to improve it. So if you click down in the link there, improve this page, you will end up on a GitHub page and then do a pull request and modify this. So it's pretty straightforward. Okay, great. This is part one. And then we have two items to vote on. One, they both concern our community communication channel. Currently, we are on Slack, but we consider to move to Discord. And so if you prefer that, just for the communication of typing text messages, then put a Y there. Or if you dislike this idea, put a no. And the second question is, currently we are using like here Teams for meeting recordings and so on, and we could also move that. And maybe Romeo, for 1 second, you can detail on this, how that would work. So I guess OBS Studio would be for the recordings, but maybe Romeo, a couple of sentences on that.
Yeah, okay. Yeah, so the idea is that we have a single channel also for the registration. We have the invite link, because at the moment everybody has to ask me and I have to like send invites and put it to the Slack channel, and Slack doesn't work for everybody. And on Discord we have then one thing, because you have the text messages and you have a separate channel where we can have those monthly meetings, and recording is then be done by myself or someone else. I will assign this task to. It's basically a screen recording and the audio, and we will provide the recording the same way we are doing it now. And yeah, you can just vote yes or no, or don't vote. It's a democracy here still.
Okay, great. And a little bit of background on the Discord channel is, so Miko, maybe he's there, I'm not sure. You can also say a couple of words about it, but it's essentially a setup that from the Asterisk Labs, it's the startup in the UK. They were so kind to invite us to that community. Yeah, please, Miko, if you want, just add a couple of thoughts, because it's not exclusively the Earth2Vec channel that is there, but there's also a couple of other ones. Yeah.
Yeah, absolutely. Sure. So to be very specific, it's actually precedes Asterisk Labs, this Discord. I think we set it up like 2 or 3 years ago with Robin from Satellite Image Deep Learning, and was just a Discord for chatting about satellite image deep learning mostly. It's like semi-dormant. You can see that there's not that much activity, but it usually works well for communicating on various topics. And it's quite easy to adopt it. So we have like multiple sub-channels for Earth2Vec right now. So hopefully, like if we do move some of our activity there, we can have like a separate channel for tracking meetings and making notes for the meetings, a separate channel for like more casual discussion. So I think it might work quite nicely. Like we can see how it goes. But in any case, like we're like, I think I'm the only active moderator of that Discord right now. So we have like a lot of flexibility, and I'm hoping that it can be useful for Earth2Vec as well.
Mm-hmm. Great, thanks so much to give us this platform, because then you have a kind of like also democratic way of people easily joining and so on. So it's very nice. So one last thing we have to check is our next meeting will happen on December 12th. Is there anyone who volunteers for moderating this round? Don't be shy. I'll be there as a backup. No one pops up, but it's maybe good to rotate so we see multiple faces and multiple people being active.
If it's the first Discord meetup, like I'm happy to run some tests before, but on the 12th I'll be away, so that's why I can't volunteer myself. But for the next one, I'm happy to take over. But in any case, like if we want to do some technical runs, if we move to that, we can do that before I'm gone.
Yeah, good. Okay. All right. So there's an option to moderate next time. I'll be there as backup, and we take it then maybe from there. Then, yeah, let's dive right away into our focus topic for today. So we are very happy to have Marc Rußwurm here from Wageningen University in the Netherlands. And he will talk about learning mental maps in neural nets. And yeah, technically, as I briefly mentioned already, this concerns implicit neural representation that are also a nice way to kind of like summarize raw satellite data and compress them into representations that are even smooth across coordinates and time. So Marc, thank you so much for joining us, and take it away.
Yes, thank you very much for the nice introduction. It's a pleasure to join this community and present some of our works here. I think I can talk about a bit of a complementary field of implicit neural representations to a lot of the compression work that I know that you're doing that is like really nice. And with these slides, I aim to give a bit of an overview of like advantages, disadvantages of different type of embedding approaches, and also sprinkle in like quite a bit of related work in different papers, but also some of the research that we've been doing like collaboratively, but also within Wageningen. So let's start with a video this time. Have you heard about GeoGuessr before? Yeah? So it's an online game, and let's have a look at one of the best GeoGuessr players on the world.
Mexico. Wait, no, this is the same rock that was on that one island. What island was it with this rock? It was the island between Inalai and Guam.
Bang, 7.5 kilometers guessed from just basically one single image. Quite impressive. And
Mexico. Wait, no,
let's not play it again. And if you're a bit on YouTube, you may have seen some of his shorts. So he memorized basically a lot of patterns, geospatial patterns all over the world. And just because that particular type of rock is present on this individual island, he could really accurately geolocate that place, which requires both a visual understanding of what we are dealing with, but also a very good fine-grained mental map of what patterns do we find all across our planet. And if you take this example here, we see a city with several like roofs and streets and so on. We may see there's a castle on the hill. We see like fairly large regular grids. So those are the patterns that we can extract from one particular image, like satellite data that we think we are fairly familiar with. But then there's also the second aspect of location and what concepts do we associate with a particular location. And we may know that medieval cities are more than 500 years old, so it must be a fairly large city if it's been already there 500 years ago. We also see that other layouts, so there's some history in the 18th century. And if we play this geolocalization game, we basically match our what we see in our vision with our eyes with our mental map and our understanding of the world. And now with machine learning, we can of course start to play the same game and build basically encoder models to also geolocate images. And where I want to go with like slides is that we learn really interesting intrinsic patterns from doing this. So what we can do is we can use a CNN or a vision transformer to get visual pattern embedding. I get to use a pre-trained remote sensing model. These geospatial feature embeddings will describe basically that image for us. And we can also build a location encoder, which I will go into a bit more, which is a small neural network that encodes geospatial patterns in its weight that inputs coordinates, outputs a vector, to bring both in the same feature space to then do basically retrieval and select the closest match between coordinate and location. But before I go into the individual parts, I want to zoom out a little bit and talk about the bigger picture of what are we doing here basically in the first place. So if we are asked to describe this particular place, the classic way to do that is basically by collecting more and more physical data, installing sensors, describing the image by text, getting RGB image as we see here, but also installing temperature sensors, measuring the elevation, all of these like explicit data that have coordinates that we're collecting. But with embeddings and with deep features and deep learning, what we can do is basically have a complementary way to augment all of that existing data that we collect with patterns that we can extract from the images that basically focus on what makes this particular location unique. And this is where geolocalization comes in as a quite interesting task that we can actually optimize for. And if we think about embeddings on a larger scale, what we can use them for, there's like several functions that are interesting, and so that basically applies to both image and like location embeddings. We can use them to compress big geospatial data that I think you're very familiar with, fusing also different data modalities, but also interpolating between different geo data sources, and ultimately also provide a vector layer that can also help to interoperate between different machine learning models. So let's go back to our geolocalization objective. And I structured my talk basically according to these three parts. So let's briefly talk about pre-computed embedding fields, or like remote sensing foundation models, how to basically extract patterns from images. Then I'll focus more on the implicit neural representation part with neural networks. And finally, I want to bring everything together with geolocalization as a training objective and some works in that direction. So let's go into this first part. And you may have heard, or you're fairly familiar with remote sensing foundation models that are now fairly broadly available, that basically encode a wide range of different remote sensing modalities across space and time and spectrum, basically for two individual feature representations. And this is basically where I want to go with this. A nice view of this is that these remote sensing foundation models, that they compress the geospatial data that we have that is usually very correlated, like neighboring pixels being very correlated naturally, to a more condensed feature representation that then can be fine-tuned with like fairly small classification heads like linear regression or KNN for a variety of downstream tasks. And the key feature here is basically to keep the foundation models frozen, because we don't necessarily want to touch them if they are like really big and complex, or maybe even distributed across multiple GPUs. And by having these embeddings available, we can solve tasks with very small and lightweight downstream models. Yeah? And this is where a kind of advancement towards pre-computing these deep features come in, that we basically take the raw geospatial data like image rasters, we put them through frozen remote sensing foundation models to get these feature representations, and then we can store these feature representations basically as another data layer in existing embedding databases in a discrete form, which makes them really usable for downstream users, because everybody is fairly familiar with doing normal classification on some features. It's not a big step to then use deep features or embeddings from existing like infrastructure like Google Earth Engine, and then run downstream tasks without needing any particular knowledge of deep learning in the first place. So very nice direction. And that's also where recent works like Alpha Earth embeddings play in, that build a very complex model, train on large data, and then provide the 64-dimensional embeddings in Google Earth Engine ready to download, or similar tessera embeddings which focus on time series data and pixel-wise time series that you can also download with an API. And I want to give you some example here from research from a master student, where in Wageningen we focus on environmental topics like tree species identification, and it's actually a quite challenging problem because label data are really hard to come by. There's people who go into the forests and then measure basically individual trees. So across the Netherlands, in our case, we had only 462 pure plots of that tree species is present in that location. And the classic approach, also published last year, so like state of the art in that particular domain area, is basically to fit different sine and cosine functions through these time series of Sentinel-1 and Sentinel-2, and then to put that into a random forest. So valid approach, but the question is, what can we do with like deep feature embeddings? And what we did is we compared this classic approach from Fancini with embedding approaches with a Presto, a lightweight time series model, and then these static alpha Earth and tessera embeddings, and then basically either fine-tune only the MLP, or in Presto we actually also try to fine-tune the entire model. And the key takeaways, I think, are quite interesting. We had two different tasks, one a bit more challenging with 13 classes, the other one being 7 classes. And even like the deep features from Alpha Earth and Tessera, they got better accuracies than the random forest on the harmonic features, because it's just very hard to design features for time series. So that is a nice observation, to then basically just download these pre-computed embedding features, and you get a better performance than a state-of-the-art model from last year, which is nice to know. We also use this lightweight Presto model that by default, or like in a frozen way, didn't give us particularly good results, but because the model is fairly small and easy to use, fine-tuning it further. So if we put in our knowledge of deep learning, basically further training it, then we got accuracies that are actually better than the frozen embeddings. So if you're up to best possible results, it's probably still good to not just use the embeddings, but fine-tune these models further. But I think for a simplicity approach of just doing a random forest classification on pre-computed features, it's already quite impressive what we can get out of the box by just downloading fixed features. And with that, I also want to close this first part. So to summarize a bit, how can we basically capture this visual system? We have all of these different geospatial data layers. With these pre-trained models, we can get deep features in a compressed form, and there are common ways to call them embeddings now, and then store them in a pre-computed embedding database, which I think primarily is extremely user-friendly and makes these deep AI models very accessible for a wide variety of practitioners and researchers who are also not versed in Python, or don't know how, or don't want to learn how to train individual models. So I think it's a great tool to make these models really more accessible. But like in the beginning, we basically extract patterns, visual features from data that are relevant for pretext tasks like mask autoencoding or contrastive learning. But the way these foundation models are trained, they don't necessarily capture what makes a particular location unique compared to other locations. And to go back and take this as the geolocalization objective that, in this case, I'm very interested in, we need to have the second aspect, this mental map of what are the patterns that we find in different locations. And that's where implicit neural geo-representations come in as a different way to represent geospatial data and store data in basically a neural network. And implicit representations are a field that has come up, for instance, in computer vision and neural radiance fields that some people might have heard of, where this scene of like a 3D truck basically is not stored as a mesh or like as a voxel grid, but is the information is stored in a neural network weight. So how do they do this? And the way nerves are trained is you have different images from different perspectives of the same 3D scene, and you train a network to input coordinates and the direction of the light ray through the sensor plane, basically, into a neural network. And then a neural network then outputs you RGB and like a transmission factor. And you can train this because you have different images, you have many pixels, and what you get is basically a neural network that then can interpolate between different viewpoints and give you the pixel values that this new position would give in terms of which RGB values would be visible from this new position. And as you've seen in the previous slide, it's fairly convincing on a small scale to really represent 3D data in network weights. And the same we can do in geodata as well. We can define a small neural network that inputs some coordinates, longitude, latitude, for instance, and then predicts a value at a particular location. And then if we have a ground truth value, like in this very idealized case, land-ocean classification of land being 1 and ocean being 0, we can basically train this neural network to basically reproduce these points and reproduces a value of 1 over land and value of 0 over ocean. But interestingly, what these neural networks can do is they can continuously basically learn this underlying function. Our world is continuous, and when sampling geodata like raster and polygons and points, we are basically sampling individual points, and by learning to approximate them into a neural network, we learn again a continuous function of our geospatial world, which is like fundamentally quite interesting. And what we can do now in this neural network when we train it over multiple epochs is we see that the underlying network approximates this land-ocean function of our world fairly well. So that's a fairly constructed example, but there are some more real-world use cases, in particular in species mapping. So you may have heard of like a naturalist and other tasks where you have species observations of the blue bird is located over here, the red bird is more located over there. And these are individual point locations that have a probability of presence of 1 for the species here and then 0 of the others. And there's a line of work that basically learns such a neural network to input the coordinates and then output the probability of the species being present at these particular locations. And what you see is basically when you then input coordinates that are not exactly on these support locations, but in between, the model is able to interpolate between your training and support points effectively. Yeah? And what makes this a bit attractive compared to other interpolation methods like kriging and bilinear interpolation is that basically you have your training data encoded in the neural network weights, and so forward inference becomes really fast. While with kernel-based methods like kriging, you always have to look up your training data and calculate similarities to your closest neighbors, etc., which is conceptually complex, but also scales not particularly well. But one interesting feature that here Elijah Cole and others reported is basically if you then take an intermediate layer, so not the last layer of the species probabilities, but intermediate layer, and you make a PCA visualization on this higher dimensional vector to like 3 RGB channels, you will see patterns that follow natural topography. Yeah? So you see like the Rocky Mountains down there, the Andes Mountains, just basically from the supervised loss of which species are there. From that supervised information, the model inferred some environmental biotope-like information about our world, which is a nice addition that they had in their paper. And that, of course, continues, like working with few shot samples and text prompts is a logical next step. But let's take a step back and talk about computer vision again and other fields in implicit neural representations. And one lesson learned from that field is that if you basically want to encode data in neural network weights, it makes sense to add sign activation functions into the neural network. Because usually we use ReLU functions for classification and regression. But ReLU is really good if you want to do classification, because you zero out a lot of irrelevant features and you're only really left with the features that matter for your particular task. But we want to do something different here, right? We want to represent data implicitly in neural network weights. And here Vincent Sitzman et al. Showed nicely in the Siren paper that sign activations are basically making it easier for the model to learn an underlying data, like here this video of this cat where you see the ReLU versus Siren comparison. And the analogy here is to Fourier sequences and Fourier decomposition, that if we have a signal, a time signal in this case, we also can represent it in terms of coefficients and sine and cosine basis functions. So I think seeing Siren as a multi-layer Fourier decomposition makes a lot of sense, and because we're using neural networks then in a different way to how we would do it usually for contrastive learning or classification or regression. Good. Another lesson learned here is also that it makes sense to, if you want to input coordinates into a neural network, it makes sense to first encode coordinates, not as like small barely changing values like longitude, latitude, but to basically spread it out over many dimensions through positional encoding functions. Again, with sine and cosine functions of increasing frequencies. And here the Stančić paper, also from the INR works, show very nicely here in this example, if you want to represent the RGB values of a pixel only based on the coordinates of the pixels, adding these sine, cosine, positional encoding layers in the beginning that don't have any trainable weights per se, also makes it much easier for the model to learn the underlying data. What we see here in the ReLU example is actually we see a lot of triangles and so on, which is a clear artifact from the ReLU model that is behind this. Good, and that's also reflected in the geospatial world. So there is this review of Genshin Mai on location encoding and GeoAI, and what is also nicely summarized is that it makes sense to have a positional encoding function without any trainable parameters in the beginning to spread longitude and latitude out across many dimensions of increasing frequencies, and then input them into a neural network to either produce a scalar, if you want to have a species probability or sea ice thickness, or you can also choose to output a vector representation. And one way that makes sense for like the spherical geometry of our Earth is not to necessarily use sine cosine functions, but to move to spherical harmonics, which are orthogonal basis functions of increasing frequencies that are nicely defined on the entire Earth and don't cause any artifacts on the poles. And in the Earth sciences and like geodesy, Earth gravity, spherical harmonics are already used since like many decades. And you can see them as a spherical variant of Fourier signal processing. And what we have is basically a set of weights that can be determined based on observations, and then these basis functions that are increasing. And in theory, if you have unlimited number of these basis functions and weights, you can approximate any function on the sphere. And that was a bit the underlying idea of a paper we had in like 1.5 years ago. It's getting a bit older, but still hopefully a bit relevant. So it's basically to follow this idea of location encoders and use spherical harmonics as the basis functions in the positional encoding, and then Siren as the neural network in the second part. And we have basically different ways to control the resolution here. One is the number of harmonics. So if we increase the number of spherical harmonics that we encode the data with, we can increase the resolution of the underlying signal. And also if we increase the complexity of the neural network, basically from a one layer, the linear layer, to like a multi-layer perceptron, like not too deep, there was 3 to 4 layers, we can get much higher resolutions, but obviously not like super crisp at this particular scale. And one takeaway here that maybe matters if you want to input coordinates in a network as maybe a conditional variable is if you input coordinates directly into this network without any positional encoding and without any sign activations, it will give you a benefit, but there are better ways to do it. So here we see a naturalist species classification accuracy, how much additional accuracy we get by adding coordinates, and for just inputting coordinates alone without any additional processing, we get like 9.3%. But if we basically use a positional encoding model with spherical harmonic basis functions, we get like up to 12.3% accuracy, so quite a bit of like 3% benefit. And importantly, also we get fairly good fairly good accuracy just on using a linear layer, right? So if we use a good basis function representation, also a small neural network works well. And simultaneously also, if we use a neural network with sign activation functions, even putting in coordinates without any positional encoders or without siren, also got us really good results. So that kind of questioned a bit this dichotomy of positional encoder and neural network, but it was a nice analysis paper in that direction. So some small takeaways from that individual paper on implicit neural representations with spherical harmonics is in any problem where you want to have if you have a neural network, you want to input the coordinates, just adding a small siren location encoder there to input the coordinates before you put the features into a larger framework makes a lot of sense. And if your data is global, and especially if you have data on the poles, then spherical harmonic basis functions make a lot more sense than sine and cosine basis functions. But zooming out a bit, the larger takeaway here is with implicit neural representations, we store data in a different way. We are very familiar with rasters, points, lines, and polygons and other geospatial primitives in a discrete form stored in a well-established spatial database that we know how to implement and that it have been optimized for like 20 years. But with neural networks, we enter a new way, a different way of storing geospatial data in a continuous functional representation, which is of course not yet as optimized and as such a high resolution and so on. But I think it's at least I find it a very interesting research direction to follow, and especially if you want to condition models on larger scale type of phenomenon. Good. Zooming out again, third step, zooming out. So if we want to solve our geolocalization objective, we can basically encode the image to a feature representation through like remote sensing foundation models or pre-computed embedding fields. And we know how to build basically now a location encoder that inputs longitude, latitude, or also optionally time, and put that as a value, or also put it out as a vector. And now the third part is basically how to bring those two aspects together to use geolocalization as a training objective. And that's where I come to a line of work that is based on the clip laws and particular SAT clips. So geolocalization via satellite contrastive location image pre-training. So we have a lot of geospatial data that the unique property is that they have coordinates describing them in the metadata, right? So what we can do is basically play out this geolocalization example from the beginning, put the images through an image encoder, get a vector, put the coordinates through a location encoder, get a vector. In the beginning, that vector will be very random because the location encoder is not trained at all. But then we can use the clip objective to basically train both image encoder and location encoder together. And that's literally the geolocalization game from the beginning, because to solve this task or to get a low loss, the model basically needs to classify the correct location given a batch of images and the correct image given a batch of locations. And that's what it does over a batch of like 500 or 1,000 images. And then iteratively learn how to extract patterns from the images that are very specific to this location, and also learn a map of these patterns implicitly in the location encoder. And you may say, okay, fine, it's two different modalities. It's yet another application of CLIP. What are we doing different here to CLIP of language and text and whatever? Everybody uses CLIP nowadays. But I think we're doing something slightly different, or maybe technically we're doing the same, but the interpretation is quite interesting in a way that in the geospatial context, we can think of a lot of underlying ground conditions like social or societal, environmental, basically determining how images of our planet look like. So if you look at the images here on the right, you see some are green, some are more deserty, some are more urban, some are more full of water or full of ice. And these images appear that way because they are at different locations, of course, but these locations have different underlying ground conditions like average temperature, population density, all of these implicit factors that we could measure like explicitly, but that are also encoded implicitly in all of these images in some way. Yeah? And by basically training an image encoder to extract these visual patterns and a location encoder together, we basically learn an implicit representation of these underlying factors that make these images specific to a particular location in this location encoder. And then if we have a downstream task that is then related to the underlying ground conditions like population density or like biodiversity and elevation, then this location encoder is actually a fairly good proxy, and we can solve these downstream tasks more accurately. And at test time, which is interesting in Sutcliffe, is basically we don't need the image encoder anymore. We just use the image encoder for extracting patterns from images. But what we are actually interested in is the location encoder, the pre-trained location encoder. So that we can then basically download input coordinates, any coordinates that we like, and we get a vector that basically describes these visual patterns on the spherical geometry. And what we can see if we do a PCA representation like here on the right is that places that are far away but have a similar climate, like the east coast of US and Europe, they are similar in this embedding space because they have similar principal components, and places that may be nearby spatially, they are different in this embedding space because they have, like, one is a rainforest and the other one is more like agricultural land or more deserted. Good. And one benefit, of course, is usability. So one key feature is, of course, that these models are really small. They run on a CPU, no need for big GPUs to use them, and you can basically download these embeddings as a model from Hugging Face, which makes them quite applicable for different applications. And a straightforward use case of that is, of course, if you want to do the reverse and you want to generate an image conditioned on the location, it makes sense to give this generation model a intuition or patterns that describe that location semantically. And that's, for instance, what's done in Geosynth from Sastry Srikumar, who also use the Sutcliffe location encoder basically as a plugin for encoding longitude and latitude as coordinates. And another one from DLR, from Xenia Bittner and team, is if you want to do super resolution, it's a very ill-determined problem because you don't really know for sure what is underneath these low resolution Sentinel pixels. But if you have more contextual information of the continent and the country and the city you're in, then you can make a more educated guess on what patterns are actually the buildings, how they shaped like. And that's something that they evaluated in their model, and they also basically just plug and play the Sutcliffe encoding. And it's not the only model out there, so don't want to do too much self-advertisement. So one nice notable mention here, of course, is also GeoClip, which follows the same CLIP-inspired training objective. but on ground flicker images. So you capture a different aspect of what makes this place unique, not based on the overhead satellite view, but from the ground street view. And a nice feature that they did is to basically use the normal clip image encoder, so their feature space is also aligned with language, and they can then query basically based on different words, which is a nice feature, maybe a gimmick, but bringing in language makes a lot of sense as well. And another hybrid approach between these pre-computed embedding databases or image feature banks and location encoders is like range, which uses some retrieval augmented generation approach. To then basically query image feature banks dynamically based on a query from the subclip location encoder in their case. And this way they also basically they merge both of these principles and bring them and increase the resolution that way. Good. So now I want to talk about a few closing slides on some recent works and some like resumes throughout in both of these fields. Yeah? So in the first part, I talked about explicit feature extraction, how we use remote sensing foundation models to get these pre-computed embedding fields that are now like really usable and really broadly available. Then in part 2, I talked about how we can store geodata or data in general in neural network weights. And then in part 3, I talked about how to train those two aspects then together to basically learn an embedding representation that is extracting uniqueness patterns and store them in this location encoder. And there's basically these two complementary approaches of storing and representing and generating approaches. So we have this explicit feature extraction with these foundation models, and that are really nicely compressed representation of a lot of raw, highly correlated remote sensing data. And I think they can serve as a really good drop-in replacement for many application areas to the raw data, or also support additional raw data to the with more modalities. And then on the other side, we have these continuous embedding models that are more served as models and not as individual embedding vectors, because they are so small that you just need to put in coordinates and you get a vector. And these are downloadable via Hugging Face and also fairly easy drop-in replacements into larger frameworks if you want to condition your model to a location. The first are generally more high resolution because they operate on the resolution of the underlying data. The second are generally more low resolution because we're limited by the capacity and we cannot store a terabyte of geodata in a small MLP today. And that will be a challenge to be solved. Here's some other follow-up work since then. So is there one embedding strategy to rule them all? Of course not. It depends, like always. So we had a master thesis last year where we looked at Spain because we had some disease mapping data together with other environmental tasks. And what we see is the image encoding features, the explicit features, work really well for really good visual tasks at high resolution, like land cover classification, like here. So for visual tasks, image encoders work better, which I think makes a lot of sense also because they're really high resolution. But when it comes to more indirect tasks that are much more larger scale or contextual, actually the high resolution of the image features themselves, they were too fine-grained. They were a bit too noisy to really get good results. So in these cases, for more contextual tasks, the subclip and geoclip models performed better because they were more smoother over larger areas throughout. And temperature was kind of in between minimum maximum temperature. Another paper that just came out on arXiv is from Arjun Rao, where we basically analyze the intrinsic dimension of existing embedding models. And one key feature is that we can calculate intrinsic dimension on all types of vectors, so no matter if it's location encoders or image encoders. So that's a way to interpret these embeddings in a way that is quite universal and independent to how they are actually originally calculated. So it's a really nice analysis tool. And one thing we see is that even though a lot of embeddings are served and provided at a really high ambient dimension of 256 dimensions or like 2048 dimensions even, if we calculate the actual intrinsic dimensions that are captured in the data themselves, the dimensions are actually much lower. So for location encoders, they are like roughly around 10, depending on the way how you calculate them. And for image encoders, they can be like around 20. Yeah? So there's more information in these image features because we have more intrinsic dimension, but also it's not a technically very well compressed representation. Because if you really want to have a efficiently compressed data, you would want to have the intrinsic dimension similar to the ambient dimension. But for the downstream task, it doesn't really matter. Neural networks also like redundantly encoded data across multiple dimensions. So not a big deal for the downstream tasks themselves. And one nice feature that you also found is that if we calculate this intrinsic dimension locally, we see geospatial artifacts. So if you look at GeoClip, which is trained on data that is predominantly from US and from Europe, you see that also in these areas, the intrinsic dimension is larger than in other areas that are underrepresented. And we have basically two metrics. One is representativeness, which is the intrinsic dimension before fine-tuning, so just of the embedding themselves, and that really nicely correlates with downstream performance, which is a really nice proxy if you for some downstream tasks, or probably for most of the downstream tasks out there, that if your intrinsic dimension is larger, then you're also most likely to get better results on downstream tasks. And the other counter example is task alignment, where if you calculate the intrinsic dimension after the model has been fine-tuned to a downstream task, the lower the intrinsic dimension, the better your downstream performance will be. So I think that's very interesting because what it sees is basically how well can a model collapse all irrelevant features and patterns away and ignore them and only focus on the one or two dimensions in this high dimensional space that is relevant for your classes. So in a binary case, technically, if your embedding model is able to collapse all of these features away to one axis, you have a nice binary classifier of here on this axis and there on this axis. So nice work that I'm happy to feature along with other works, and I'm done now. Thank you very much. Here's some links on the location encoding work from last year, then Sutcliffe, and also Yoon's recent paper. So thank you very much, and happy to take questions and all of these. So thanks again.
Thank you so much, Marc, for this comprehensive overview of your work and also linking to others that kind of are active in that field. So we open the floor for questions. So I think you just unmute yourself and feel free to ask a question if you have one. Right, so while you're thinking what to ask, maybe I start with a question. Oh, I see someone raising his hand.
Yes.
Daniel? Okay, Daniel,
I am
please go ahead.
Daniel Wiesmann from Development Seed. I have a question about talking about these embeddings as compressions. Because in some ways, if you think about it, if the embeddings are really as good as we want them to be, they're a positively distilled version. So they might have more information in them than the raw data. And so in some ways, because it's already, I'm thinking about that in terms of like, if you want to compare two sentences in language, it's really hard. You can't just match words, right? Like they have the semantic meanings. And so if an embedding model captures the semantic meaning, then it's not really a compression. It's actually building in a lot of knowledge into the sentence that isn't explicit in the data. It's like the semantics, the meaning of a sentence is not necessarily explicit in there. And you can only understand it if you know more than that simple sentence, right? You know language. So can you maybe comment on that? Like I feel like talking about embeddings as compressions is a bit too simplistic. That's the point.
Yeah. Yes, I like this analogy with language, but I'm wondering, I mean, I feel ultimately you cannot get more information out of the raw data you have, right? So I feel in the language case, there is a lot of semantic information captured in these individual words that are not hard quantified, but then are then used as the additional information to compress out. But I'm not an expert on compression in the first place. I think especially in this room, there's people who are much more versed in that. My feeling is also compression is one of the functions. So from a technical view, it makes a lot of sense to compress data in an efficient way, but if we think of masked autoencoding and SimCLR and the way that these models are trained, those current losses, they are not really optimized for compression. So with masked autoencoding, we want to reconstruct the underlying signal, but there's nothing in there that really says you should reconstruct it with as small of a bottleneck as you can, or the SimCLR the same. And I think that's what we kind of see in the in like Ayun's results on the intrinsic dimension, that compression is one aspect, but if compression is your only objective, I think you need some additional losses, or like you need to, let's in a stupid way, maybe PCA the embeddings down to have it as efficiently compressed as you can. But with that, I don't want to say more with more people here knowing more about this field than me.
Yeah, I was trying to be a bit provocative here. So
provocative is good. That causes discussions. Good. I see online.
Yeah, I can maybe add a little bit to the compression piece, in the sense that, yeah, there's typically this extra loss that you can add in terms of entropy encoding, right? So we also want to make sure that that embedding space, the distribution of your feature vectors is such that you can efficiently encode them into a bit stream. So that it goes on top as an additional loss. But it's true, yeah. There's a shared overlap of compressing data nicely with these models, and but also the semantic aspect that maybe goes beyond pure compression makes sense, right? So Daniel is essentially saying the entire information that is available in all of the data is maybe ingrained in that model. It's not only compressing that single input image that you put through. And if you have more modalities, as with geolocation, for example, as Marc was focusing on here, you get even more information into that picture, right?
Did you measure, if you add this entropy loss for more efficient compression, does it have a negative impact on downstream tasks?
I mean, we were still experimenting, and in general, what I would say, the architecture itself also tells a little bit how well the downstream tasks perform, right? If you have an encoder decoder structure in terms of auto-encoder, then semantic segmentation works better. If you do contrastive loss tasks, then maybe image level tasks work better. So it's very much depends so far. So that's what a pattern I see. Let me follow up with a question. Or Daniel, do you have anything else to add, or do you want to? Okay. Anyone else who wants to chime in?
Yeah, I have the hand up. This is Bruno.
Yes,
sorry, my
please
connection
go
is
ahead.
not that good,
Bruno.
so it's without video. I want to double click on what Daniel said, because I think it's also very interesting. So Daniel, am I understanding correctly that you're saying that it's not just a compression, but also a projection against something that is not in the data? So you are leaking or using something that is not in the data itself.
It's a bit the question. Like I would say a good model will be able to put connotations on, if you maybe in language, for me it's easier to think about. It might be able to add connotations to a sentence that isn't pure information and it's just in a sentence in the words themselves. So the tone of it and stuff like that, like there's subtleties there that a model might embed somehow as like, these are 3 options that could be meaning out of this pure, like, bunch of words. that might be a bit beyond what's actually just only in the words themselves, like kind of pointers of what this could mean. But I don't know. This again, like this is just speculation, right? I have no.
What would be the implication of that? Are you seeing that as a limitation of embeddings or as a feature of embeddings?
I think it's a feature, and it's kind of a thought that I had that would be interesting to investigate a bit more in some ways. I don't have time for it, but that's I feel like I think the provoking thing is like, don't just call it compression, because I think there's more going on than the intention. Again, as they said, like it's not about just making it really small. There's other objectives. And compression just has the objective of making something small, and that's like a fundamental difference here.
Yeah, Nico, just my comment, and I'd love to know what you want to say there. I like that idea that is not just compressing in the sense of signal, but also projecting into some other dimensions, giving more or less information. It's like a compression with a dictionary. And the dictionary is the method by which you did the loss. Anyway, I like your comment, Daniel, and Marc. Thank you for also.
That's actually a good topic to continue on in our Discord channel, right? So that's a very good way to continue that. Yeah, that's also our kind of aim, that we try to spark these discussion and connect people. Very nice. Yeah, good to follow up. I am also interested in that, so let's follow up on that. I see also Miko raised his hand. So Miko, please.
Yeah, it's on the same topic really, but I think I think it goes back to what we define as embeddings. Like, I like to think of embeddings as just like useful projections, which seems like a very shallow way of describing things, but like compression is just one of the effects that you get from the prior that you kind of encode into the process through the architecture, right? Like if you make the architecture and the losses this or that way, you get a bit of compression, right? But to me, it's embeddings are just a projection of data that makes it somehow more useful for some specific scenario, right? And I think it goes back to, I remember like a comment on LinkedIn, like maybe months back from Bruno under one of my posts, like from when we released some of the major term embeddings that were actually like took more space than the input data. I think it was Earth, that if you don't downsample and like get the spatially distributed features from the model, you actually get an embedding database that's larger than the original data. And I'm not saying that Earth is unique in any way, or that like these specific features are that we released there are like unusually interesting. But I could imagine data sets, because I haven't experimented with that much, but like I could imagine data sets that take more space than the input data and are still useful. And like you can just imagine, and going back to the like sentence and analogy, like you're just if your data volume inflates when you embed, it just means like you're feeding that prior from somewhere else. Like Marc said, like you're not, there's only a limited amount of information in the signal, in the observation, but you can feed sources of prior into your embedding to basically make it bigger, right? So like if you just combine some information that you learned before, I don't know, if you learn something about the remote sensing image and you learn that, I don't know, if there's a street that usually continues further away, right? Like, so you're actually like making a lot of additional links to describe your data in a more useful way. And same with the sentence, right? If you've heard many of this like human generated sentences before, you can ascribe a lot of additional features and assign it to an embedding of a sentence. Like you can say, oh, someone's being sarcastic here, right? And it in many like compressive embeddings of that some sentence, you don't get this information readily available. But maybe if your model adds this additional prior and adds it in a easily digestible manner to the embedding, your embedding might actually occupy more space than input data. I see Jonathan's hand up, so I will stop rambling.
That was very interesting. I actually wanted to bounce off of that. We're doing weather downscaling and using embeddings, and what we see is that the context around the pixel is very important. And so I think exactly what you're saying, like you get more information than just the information at the pixel itself. With an embedding, you get all the context around that pixel as well, that is embedded in a given vector. So yeah, I agree with you. I think even if the downstream product has more it's more voluminous, it might actually include more data or more information.
Yeah, I think what's also interesting here is that the data we use is also just a projection of our world. So there is a lot of information out there that we capture on like basically pixels, but extracting patterns behind these images of the actual world, that's also a good source of additional information. I mean, it goes into this compression discussion, but on if we move to the language case, words have a lot of semantic meaning because we use it to communicate very minute details, and that's a lot of information that is stored basically just within the meaning of a word, and then we encode the word as a simple one in a list of vocabulary. So in that way, it's just a one in a vocabulary, but actually the meaning is much deeper. So in that way, maybe the underlying information gets more than just the word, the index, and the vocabulary. So something similar, I feel, is happening here, that we have our continuous world out there that we capture with the data, and then by building smart models to extract patterns, we extract patterns that are of the world. Okay.
Yeah, cool, thanks. Any other questions? So Marc, I have one more thought I was thinking while we were talking. So essentially these implicit neural representations, they kind of potentially smoothly interpolate, no? And there's no kind of grid anymore associated. You can input any coordinates you like. And I just was wondering, have you looked into how sensitive this interpolation is to your model architecture? Is there, so I guess as I also feel like this might depend on in the training phase where you sample images, essentially, which locations you show to the network, how close these locations to each other are. So what about the sensitivity of these interpolations based on the pre-training and training you do? Can you share some thoughts there?
Yeah, I mean, there's no grid per se, but there's a lot of inductive bias in the model architecture. So all of these have a position encoding. There's a maximum frequencies you want to encode. So that's a hard-coded smoothness that you put in. So if I go to this siren example, basically, we have control of the underlying resolution by choosing the number of polynomials and how deep we make that network. And what is the optimal smoothness of this interpolator? That depends, of course, on the data. We don't want if we have data sparsely distributed, we don't want it to be very high resolution, because then it's just meaningful right around the support point and not meaningful anywhere else. So there is a sweet spot of this interpolation smoothness. So it's not a grid, but there's parameters that determine the resolution, which need to be tuned to the task. So there's no perfect world, of course.
Yeah, no, I was a little bit more thinking about why you train. You will train on some data available, and they are distributed globally, not on a grid, but kind of like, let's say, on a mesh. And how sensitive are your interpolations then in areas where you have only very little amounts of data? What does the interpolation mean? So I just want to get a feeling of, so there's this thing, you don't have the grid, you have the smooth function that interpolates. And the question is, what's the characteristics of this interpolation depending on the data you train on in the beginning that has some geospatial distribution and the architecture that you use?
It's a good question. So first, our main goal was like global coverage, so we collected data uniformly. But when I'm thinking of let me pull up this one here. If we're thinking of GeoClip, where there is data specifically in the US and Europe and not of others, the predictions of the model in these other regions without training data will be much more close to random then, right? Because if there's the models are all randomly initialized, and if there is no data there, it will stay on the more initialized way. Of course, there's a lot of science and all of that, so a lot depends with everything else. But the more bias you have in the data, the more uncertainty or poor performance you may have in areas where you don't have. But I don't know if that is a particularly good answer to your question. I feel I'm deflecting.
It was an exploratory question out of curiosity, so nothing. I don't expect any definite answer. I was just curious because you work with these, and I want to get a little bit of gut feeling of your understanding of this so far.
A key question will be, so far these smoothness parameters we define globally based on the global data set, but our geodata doesn't work this way, right? There's much more data in that area than in this area. So we can either blindly make models larger and increase the capacity, but that's not very efficient. So being more flexible on having resolution where we need them is a good way forward.
Good, great, thanks so much. Anyone else has a question? We are over time, and it was very exciting discussion. We can also continue to do that offline on our community channel, and feel free to reach out. But if there is no more question, do I see any more questions from people who are still there? I don't see any raised hands. Your last chance, I would say.
Yes.
Oh, there's one. Yes,
Hello.
please. Yes.
I have a question. Last question. Did you consider to train your model on a different type of projection, such as like a EPIX VGS projection? Because
no, because we were aiming for like the spherical geometry in the first place. And I mean, we assume the Earth is a sphere, which technically is not true. It's a ellipsoid, but in approximation, it's valid. And going to projections makes sense if you always lose something in projections. So a common way that is much easier to implement than spherical harmonics is, of course, sine cosine encodings. And if you choose a projection, like let's say you work on the polar data, and you don't want to deal with spherical harmonics because they are a pain to calculate at high resolutions, which I fully understand. You can also choose a planar projection on the poles and then work with sine cosine functions that will work well there, but then you will get artifacts around. But if your task is focused on the poles, changing the coordinate system to a projection and using simpler sine cosine positional encodings is a valid approach.
Okay, thank you very much.
Yeah, if you haven't used TOPIX, or like it's like an H3 grid. They're discrete, but they're also made for the globe in the same way.
Yeah, I mean it's a bit of a question how much software engineering and how much function math learning do we want to do, right? Because H3 grid is a very logical hexagonal grid for the globe, but I mean I'm maybe a bit on the academic bias of enjoying the simplicity of orthogonal spherical functions. And it touches my core geodesy heart as well. But I've seen location encoders working on the H3 grid definitely as well.
Okay, great. Any more last questions that we want to ask Marc? And I'm pretty sure Marc is also available through other means. I posted his webpage also on our notes, HackMD notes. You can even on Discord, so you can reach out to him. And of course, Marc, if you like, join our Discord channel, and we can continue a detailed technical discussion there as well. Anyone else? Okay, great. That was an exciting discussion today. Thanks everyone for joining, and see you all next on December 12th. Let me quickly check if there was anyone volunteering for that day. So far looks like I'm the one who's going to host it, but this is an open question until beginning of December. So if anyone wants to moderate next time, just post it in our Discord channel or even Slack for the period of the transition, or for the time of our transition. And from the polls, some people, that's 3 to 4 people kind of contributed there or voted. It looks like, yes, let's move to Discord, and also our meetings do it through OBS Studio. So Romeo, that's maybe something we can technically check. Okay, thanks everyone again. Thanks Marc so much for your time and sharing all your research. And then see you next time in December. And if we don't see you there, have a happy Christmas and holiday season, and get safe into the next year. Thanks so much. Bye-bye.
Bye-bye.
Bye.